This chapter is entitled Acid-Base Equilibria, but chapter 14, we got into equilibrium pretty quick. So I'm not sure why Zoomdal decided to separate these out. We're going to go into more detail, of course, with concepts of equilibrium and acid-base reactions. All right, when we have an an equilibrium situation, whether it's acid-base or any other type of equilibrium, there are two ways to disturb the equilibrium in terms of concentration. We talked about other ways to disturb an equilibrium, but now we're focusing on concentration. You can directly add or subtract reactants or products, and that will cause the equilibrium to shift. That's the first way, and a useful way if there's a way to do it. Usually adding is no problem. Subtracting, removing components is a little more difficult. So very often what we do is use a second approach, and that is an indirect we call it the common ion effect. In other words, if we have a component, a reactant or a product, and we want to shift the reaction, but we can't get at the reactants or products directly. Say we are more interested in subtracting. So if we want to remove one of them, we'll couple it with another reaction, say, let's say E. And usually what it'll do is produce maybe a solid that drops out of solution. And that means it's no longer actively participating in this reaction. So if we remove A, that's going to shift back this way. That's a coupled reaction. And your lab exercise today uses a lot of those couplings. Okay. Now, the common ion effect is a description of an approach that really, by definition, only has application if your reaction involves ions. For instance, if we have silver in solution and we add some type of chloride, then it's going to produce that solid, right? And that precipitates it from reaction. Now, if we wrote it, this is the net ionic equation. Probably what you'd have is something like silver nitrate, which is completely soluble. And potassium chloride would be a good choice here. Right? And that would produce this solid. And then plus potassium nitrate, which is completely soluble. So if we want to influence this equilibrium, we can add more silver, right? Cause it to shift that way. Or we can we could remove silver by adding another ion in here, like chromate, right? And this one plus that one would yield let's see, we need two of those, wouldn't we? And this is a solid. So this would remove some silver, assuming, and we haven't talked about this yet, have we? Solubility products. Okay, so I'm getting into territory we haven't discussed. Focus your attention on affecting the reaction by coupling it with a secondary reaction. And in order to do that, the secondary reaction has to have an ion in common with the target reaction. Okay, so here's an example where we have hydrocyanic acid reacting with water to produce cyanide ion and water molecules, hydronium ions, excuse me, hydronium ions. This is the true chemical reaction. If we add cyanide ions, right, the common ion there is the cyanide, and sodium is a spectator. So we add the cyanide ions, which way will it shift? Back this way, right? We're increasing the cyanide concentration. The reaction will shift to the left as written. Now, how will that affect the pH? Right? The pH is dependent upon hydrogen ion concentration. So if we add cyanide ions, then that will consume some of those hydroniums to reach equilibrium, and that should increase the pH because we're decreasing the hydrogen ion concentration. That's one way to measure the effect. You watch the pH change as you add that common ion. Okay, let's talk about buffers. In society at large, this term buffer is used to explain a whole host of different things. In chemistry, we're talking about acid-base reactions, and we're buffering the reaction. What the buffer means is when we generate a solution that is identified as a buffer, it will resist a change in pH if we try to disturb it by adding acid or base. That's what we mean by a buffer solution in chemistry. The pH doesn't remain constant when we disturb it, but it is very close to where it was before we disturbed it. In other words, the changes are very small. Most often, a buffer solution is a combination of weak acid, right? Weak acid and its conjugate base. A combination of these two in the proper proportions will generate a buffered solution. Now, you can do the same thing with a weak base and its conjugate acid, right? But most often we use a weak acid and its conjugate base. A good example is acetic acid. In solution, and I'm going to simplify this for argument's sake, rather than give you the true chemistry where we have hydronium ions and water involved. 3O2 minus. Okay, so we set up an equilibrium between this weak acid and its dissociation products. And if we have a right amount of this and this in the solution together, then we can add an acid or a base and the pH won't change very much, right? We're focused on this one when we disturb it. What happens to this concentration? So if we add a strong acid or a base, all right, after you add the strong acid or base to a buffered solution, you deal with stoichiometry first, then with the equilibrium. So what actually happens? If we have established an equilibrium and we know the concentrations of each one of these components, then if we add an acid here or a base, which removes some of those, it goes both ways, then we generally, in order to evaluate the outcome, we say what stoichiometry took place. In other words, if I add a tenth molar hydrogen ions to this equilibrium situation, then we're going to get a change, and then the equilibrium situation will follow, and we'll evaluate it from there. So let's skip that. All right. So what happens if I do add hydrogen ions? If I add some of these, add hydrogen ions, what happens? Well, we know that qualitatively, the reaction is going to shift this way. Why does it do that? Because we added extras. It's going to react with the conjugate base of the acid. Remember, this is a weak acid, so this is a very strong base. So it's going to interact, it's going to react with the extra hydrogen ions, not all of them, but some of them, to reestablish an equilibrium. So we'll shift this way. Okay. So what happens if we add hydroxide? We add a base. Well, it would react with this one to produce water. Now we know water is, when we look at, remember the reactions that occur in aqueous solution, this one is always there. Do better than that. Oh, that reaction is always there. And we know that the K for this is 10 to the minus 14. So if we add some of these hydroxyls, then the shift is going to be dramatically toward this side. That means when we add hydroxyls to this one, it's going to go to water. Almost, but not all, of the hydroxyls will be consumed until we reestablish the equilibrium. So the driving force now is this side. When we added hydrogen ions, we were adding a product. When we add hydroxyls, we're removing one of the products. And that's why the solution is buffered, because this needs to be weak to give us this strong. All right. So what we're really interested in when we talk about a buffered solution is what's the ratio of these two, the strong conjugate base and the weak acid. Because if we don't have enough of these here, then we can't get a return to this side by adding acid. And if we don't have enough of these here, when we remove hydrogen ions, then we can't produce any more of these. So there needs to be a balance between the two. You got to have some of each in that solution to be buffered. And that's where Henderson-Hasselbalch comes in. It's named after two people, and they came in historically in sequence. Henderson first was interested in equilibrium that involved these weak acids. Right? So he was interested in the concentrations of hydrogen ions. So when we write the K for this reaction, let's use a small a. Then we would write H plus and A minus over HA. Right? That would be our generic expression for equilibrium for the acid. Well, if he was interested in this hydrogen ion concentration, so he just solved the equation for hydrogen ions, right? So that gives us Ka times HA over A minus. That's Henderson's contribution to the final equation. That was his interest. Well, in the intervening years, or soon after Henderson proposed this analysis, Sorensen came up with his mathematical transform, pH. He said pH, of course, remember, pH equals negative log of hydrogen ion concentration. But we also know that this is just simply mathematics. So we can do a POH and we can do a PK also. So Hasselbalch took Sorensen's work and applied it to this equation. And if we do that, then the negative log of this one, just take negative log of the whole equation. Right? So we get pH here, right? Then we get pKa here. And this would be, we want to keep this ratio, we're not going to turn it into some kind of a p-value. We want that ratio to remain intact. So if we have this times this term, that means it's pKa plus negative log of HA over A minus. Okay? That's just the way logarithms work. But we also don't want that negative sign in there. So another thing that logarithms do is if you have the logarithm of a quotient, if you flip the quotient, instead of A over B, put B over A, it changes that sign. Remember that? Scratch your brains from way back. So now that means if we want to change that sign, we simply say plus log of the conjugate base over the weak acid. And that's Hasselbalch's contribution, and now we call that whole thing Henderson-Hasselbalch. Okay, there's the sequence, historical sequence. Henderson, 1908, Sorensen in 1909 published his work, and then Hasselbalch came along a few years later and proposed this. And this is very, very useful. If you want to find the pH of a buffered solution, all you need to know is the pKa of the weak acid and the concentrations of the acid and its conjugate base. Okay. And there's the final product. It's a very, very useful equation. The first thing we'll notice about this equation is that for any given acid, weak acid, the ratio is what determines the final pH. So you could have a very high concentration position of A minus and HA, gives you a pH. You could decrease that concentration as long as the ratio stayed the same, then you get the same pH. That's useful, especially for living systems. If you've got cell cultures or you're trying to grow things in a buffered solution. Ionic strength, in other words, the concentrations of this buffer can affect the way the cells grow. So if it's too concentrated, it might kill the cells. So you want a certain pH, but you don't want to kill your cells, so you decrease the concentration until you get something that's maybe isotonic with the cells. That's just an example. Okay. So let's take this example. Let's see, we don't need that anymore. We really only need that equation right there. That was a derivation You should be able to derive that without too much trouble. What's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? And the Ka for acetic acid is 1.8 times 10 to the minus 5. Okay. We're given the equilibrium concentrations of the acid and its conjugate base. Notice that sodium acetate is the way we're delivering into the system the conjugate base of the acid. So we know these values, right? The conjugate base is 0.85 and the acid is 0.45 molar. What we need is what's pKa? Well, 1.8 times 10 to the minus 5 is Ka. So pKa is the negative log of that value. So I just put in 1.8 exponent minus 5, take the log of it, change the sign. And I get 4.745. So that number would go right here, 4.745. And now I just need the log of that quotient. The log. And this value here is 0.2762. So the pH should be plus those two. 5.02 pH. If I did my calculations correctly. Okay. What we're saying is that this is the equilibrium concentration of each of these components. That's what that equation is based upon. Equilibrium situation. If you're not at equilibrium, then you have to calculate the equilibrium concentrations in order to use the equation. So that would require some stoichiometry. Okay. So if we have this pH here and we add acid, then we're going to shift slightly toward a lower pH. It may be 5.01, or if we add base, it may slightly move to 5.03. It won't move much. And that's what we're after. Oops. There we go. Well, that's sort of true. Buffers contain relatively large concentrations of weak acid and corresponding conjugate base. They have to have, there's a concept called buffer capacity, and I got it on a slide, subsequent slide. The higher the concentration, the ratio may be the same for any given pH in a buffered solution. But the higher the concentrations of each of the acid and the conjugate base gives you a higher buffer capacity. In other words, it can consume more of an added acid or an added base before you exceed its buffer capacity. Yeah, that's okay. There's the buffer capacity. There's a mathematical expression for this, and it's based upon the measured change in pH with the addition of an acid or a base. And come on, there it is. So we give it the number beta. So what we're saying is a change in normality. Let's see, we haven't talked about normal. Did we talk about normality yet? I don't think so. All right, normality. Or is it one of our slides coming up? Should be toward the end if we're going to talk about normality. No, I can see it there. Okay. Normality is like molarity. Right? N equals normality. And it's equal to the number of equivalents. The number of equivalents per liter. So what do we mean by an equivalent? Well, what we're trying to do with normality is express acids and bases, and actually any other solution concentration in terms that allow us to virtually ignore the compounds, as long as we're within the correct chemical reaction. For acids and bases, normality equals molarity if monoprotic. Or for a base, monohydroxyl. Okay. So if it says if you've got a 1 molar solution of hydrochloric acid, it is 1 normal. If N equals 2 times M if diprotic or dihydroxyl. So for sulfuric acid, if we have 1 molar sulfuric acid, it would be 2 normal. And for phosphoric acid, if we had 1 molar, it would be 3 normal. So once we know that, once we know the normality, then we can do stoichiometry based upon the hydrogen ions, based upon this equation. In that case, if we know the normality, we know the hydrogen ion concentration. It doesn't matter where they came from. That's the advantage of normality for doing calculations. Okay, so I said all that to go back to the buffer capacity. Change in normality, the amount of change in normality for the change in pH, ratio to the change of pH. So if we have a very large beta, that means very large change in normality of the solution will give us a very small change in pH. That's a high buffer capacity. Okay. So if we have 0.85 equivalents acid per unit pH, we can add 0.85 molar of hydrochloric acid and get only a change of 1 unit pH. That's actually a pretty big change, though. Okay. I want to draw you a titration curve. I think it'll make more sense that way. Do I have a slide on it here? I don't want to steal my own thunder. Yeah, it's coming up. Okay, I'll save it. It's got a slide of its own coming up. So, how do we choose a buffer? Well, we want to know the target pH. In other words, within plus or minus, what pH do we want our buffer to hold at or close to? if we choose the pKa of the weak acid close to that pH, and then construct the buffer based upon the concentration of the weak acid and its conjugate base, then we'll get the target pH. It's based upon the pKa of the weak acid. So for this acetic acid, we had a pKa of what? 4.5, was it? Something like that. 4.5 or 4.7. So that pKa would say, all right, acetic acid would be a good weak acid to use for a buffer that has a pH in that range, right around 4.5 or 4.7. Now that's for a monoprotic acid. If you have a diprotic or a triprotic like phosphoric acid, then you have the potential for 3 possible buffers regions because you have 3 acids. Each one has its own Ka, which gives it a different pK for each one of the protons. Okay. So a titration curve, everybody heard of the term titration? Yeah. A titration curve in this context is, for our purposes, we're titrating a weak acid with sodium hydroxide, usually a strong base. And when we do that, let's see, we get something that looks like this. I'm going to use pH on the y-axis and added hydroxyl on this one. So if we start off at a given pH, say it's acetic acid, it'll be in the neighborhood of, I don't know, 3.8 or less than 4. Then we start adding base and the pH climbs pretty quickly. But once we build up, at this point, we only have the acid. We don't have any conjugate base or very little conjugate base. Right? But as we build the conjugate base by neutralizing some of the protons off of that acid, then we get enough of them in there. So now we're stabilizing the pH. Okay. Now in this zone, this is the buffer zone, you've got enough conjugate base with its acid to buffer the solution. That's where we are in here. Then once we exceed the buffer capacity, whatever concentration it is, once we exceed the buffer capacity, now when we add hydroxyls, there's nothing to stop them. Right? So our pH just goes like that. And then when we reach the top of here, does that. That's a sigmoid curve. Okay? You see the sigmoid curve in lots of places. First place I saw the sigmoid wasn't in chemistry, it was in biology. It's like population growth. Starts off really slow, and then you reach a critical mass, so to speak, of number of individuals, and then they take off. Right? They grow, and then they exceed the nutrient supply of their environment, and they stop growing. So that's sigmoids everywhere. But in this case, we have so many added milliliters of hydroxide ions against pH. And there are various points in here. I've mentioned one of them, the buffer zone. Right? This is the buffer zone. And midway, the inflection, does anybody have calculus in you? The inflection point of a curve. This is concave up right here. This is concave down. The point at which it changes from up to down is called the inflection point. That's mathematically speaking. But in chemistry, this is called the equivalence point. The equivalence point is the stoichiometric point where the hydroxyls added equals the hydrogens available. So if you have 1 molar acetic acid, by the time you get to this point, you've added 1 molar hydroxides to get to that point. That's the equivalence point. And it will occur, depending on your starting concentration, as so many milliliters of hydroxide. 1/2 the equivalence point is right about here. This is 1/2 equivalence. That happens to be right in the middle of the buffer zone. Okay, that's the ideal position for your buffer at this given pH. Okay. So where does that actually occur in terms of concentrations? Well, there's what it looks like. And I drew this one flat, but it's actually a very gentle curve, a very gentle slope. So when we got the reaction going on here, we've got the weak acid and then its conjugate base. So at what point are we at half equivalence? Well, if we start off with this amount, now we've only got half of it left. Where did it go? Well, now half of it's over here, right? So that means the concentration of acid left in solution and the concentration of its conjugate base are now equal. So if we put that in terms of Henderson-Hasselbalch, what does that mean? If this one is equal to this one, what's that ratio? 1, right? What power of 10 equals 1? 0. So if these are equal, right? If this is equal to 1, then this term is 0. And at that point, at this given pH, the pH is equal to the pKa. Okay? That's one way that we can determine the pKa for any acid. We titrate it, find out where the midpoint is here, go over here, that's the pKa, and then we just use our transform to find out what the Ka is. Okay, I think we have a lab. Yeah, that's the next one. Okay, so how do we do all this stuff? Well, you use a burette that tells you exactly how much in milliliters of base you've added. And we'll talk about that in more detail later. But you measure the pH with a meter, a pH meter. Okay. Now, if we start off with nitric acid and sodium hydroxide, you don't really get a buffer zone. You always get an equivalence point, right? But there's really no buffer zone in here. It just goes from here like that. So you don't get a buffer with a strong acid or a strong base for that matter. We can work the titration in the other direction, and we can still get the same equivalence point for the combination of an acid and a base. In this term, we've got a strong base and a strong acid, so we're not going to get a buffer here either. So if we're going to do a titration and we want to find out what is the pH at any point in this titration curve, we can calculate it as long as we know that value for the acid, and we can judge this ratio based upon where the stoichiometry takes us. So that's why we generally do the stoichiometry first to find out where we're settled, and then we work the equilibrium to find out what the pH is. Okay. I wish every chemistry problem with that clean cut. Consider a solution made by mixing 0.1 moles of hydrogen cyanide with 0.04 moles of sodium hydroxide in 1 liter of aqueous solution. Okay, so we're given the Ka, we're given the starting concentrations. So what are the major species at the point of mixture? That is before the reaction occurs. Before the reaction occurs, we've got hydrogen cyanide, we've got sodium ions, hydroxide ions, and water. That's before the reaction occurs. Sodium hydroxide is not a major species because it's completely soluble. Hydrogen ions and cyanide ions are not major species because the reaction hadn't occurred. Plus, it's a weak acid, so they're not going to be major species. So these are the possible reactions. Remember, a couple of days ago, we looked at each one of these. And we're going to put the stupid ones in there too and then cross them out. Those two are just ridiculous. Okay, so these are the other possibilities. Hydrocyanic acid reacting with water, hydrocyanic acid reacting with hydroxyl ions, and the behavior of water itself. Okay. Which one controls the pH? Well, the pH is probably controlled. Well, we have to do, excuse me, go back to our previous slide. We have to determine the stoichiometry first. Once the stoichiometry is determined, then we can compare the first and the second equations. Okay. The pK, let's see, is 10 to the minus 10 for hydrocyanic acid. So if we compare that to water, which 10 to the minus 14, that's the one that controls. So what we have to do first is find out what are the concentrations that are left over from the stoichiometric reaction, HCN and hydroxyl. So after the reaction occurs, our major species, we still have some HCN, right? And we look at the concentrations. I should have written those on the board. Here we go. 0.1 mole of HCN. Mole of HCN. And 0.04 mole of sodium hydroxide. 0.040 mole of sodium hydroxide. So we're not going to use up all of our HCN with sodium hydroxide. That's the point I wanted to make. So if we go back to this slide, we still have some HCN left over. We have some CN minus because the hydrogen ions were neutralized by the hydroxyls. Sodium's a spectator. So that leaves us with some conjugate base. And we always have water and sodium. Oh, I hate it when that happens. I get me going and then just shift gears. We could solve that problem, right? But we're going to take a different one now. Okay. If we calculate the pH of a solution made by mixing 0.2 moles of acetic acid, 0.20 mole of, that's my abbreviation for acetic acid, and 0.03 mole sodium hydroxide. In 1 liter, right? So this is per liter. And the Ka is 1.8 times 10 to the minus 5 for acetic acid. 8 times 10 to the minus 5. Okay. Calculate the pH of this solution. Well, we look at the major species, of course. in the beginning, and then we do our stoichiometry. Here we go. There's our stoichiometry. We start off with 0.2 molar acetic acid, 0.03 molar hydroxyl, and no products. Then we use up all of the hydroxyls. And that leaves us with 0.17 molar acid and 0.03 molar acetate. And we've used up all our hydroxyls. That's the stoichiometry part, letting the reaction go to completion. Then we take the weak acid and its conjugate base and their reaction and set those up with those values that we just given them. And this is where the equilibrium expression comes in. Right, so we look at, we're saying that with this neutralization so far, we have essentially no hydrogen ions or no hydroniums. That means the reaction is going to move to the right from a position where we start with 0.17 molar acid and 0.03 molar conjugate base, and then we get this equilibrium expression with our unknowns. All right. So we set this up with our typical expression, and we say, all right, with this value being 10 to the minus 5, that X is probably going to be so small it won't affect the 0.17 molar. So we estimate. And we can calculate 5% rule. But to save time, we're going to assume the 5% rule is not violated. And our pH is measured at 3.99 because the hydrogen ion concentration is 10 to the minus 4. Okay. Now, what if we use Henderson-Hasselbalch? Well, Henderson-Hasselbalch says we're at a position where we've got 0.03 conjugate base and 0.17 acid. Plug those into our equation, and we get a pH of 3.99. So that's a whole lot quicker. All right. Let's see. 100 ml solution of 0.1 molar acetic acid. Calculate the pH of this acetic acid solution. Oh, okay. We're not doing a titration. We're just saying we have this 0.1 molar acetic acid solution. What's its pH? So we can go through our ice table and calculate the pH at 2.87. Come on, that's not a buffer. What if we want to calculate the pH? Actually, if we want to calculate the pH anywhere on that titration curve, all we need to know is what are the reactant concentrations and the P and the Ka. So if we have a 0.1 molar solution of acetic acid and we add 50 milliliters of 0.1 molar sodium hydroxide, let the reaction go to completion, right? There we react the acid with the base, and we get an equilibrium concentration of 0.0334 molar, essentially the same concentration of each one, which means that the pH should be the pKa because the conjugate base and the acid are essentially the same, 4.74. Okay. All right. What if we have, okay, fly in the ointment? What if instead we have a weak base and it's conjugate acid? Well, in this case, we have 0.1 molar ammonia with a Kb of 1.8 times 10 to the minus 5, and we add 50 milliliters of ammonium chloride. All right, so we're adding ammonium, the conjugate acid, in that amount, and we've got 0.1 molar ammonia to start with the Kb. So we can still do, well, we haven't, okay, so we're adding a certain amount of each one. How do we get those concentrations? The initial concentration of ammonia is 0.1 molar, 100 milliliters, 0.1 molar of 0.1 molar, and this is ammonia. Okay, if we multiply those two together, we get 10.0 millimoles. If you take milliliters times molarity, you get millimoles. Okay, now I'm going to prove to you that that's right. If we actually take this and say, all right, if that's molarity, it's moles per liter, right? So this is 0.100 liters times 0.1 molar. So that would be 0.0100 moles, right? So what's milli? Milli's 10 to the minus 3, isn't it? 10 to the minus 3 would be 1, 2, 3. 10.0 millimoles. Okay. Sometimes it's more convenient to use millimoles. And if you have millimoles of something per a certain number of milliliters, that gives you molarity. Millimoles per milliliter, right? The millis cancel, moles per liter. Okay, so we have this many millimoles of ammonia. But what's the final volume? We added 50 milliliters of the other solution. So this divided by 150 milliliters equals 0.0667 molar in ammonia. That's where that value came from. And we can do the same thing for the ammonium ion, right? Because we added 50 milliliters of 0.1 molar ammonium. So that would be that'd be 5 millimoles per 150, and that gives us 0.0333 molar. That's where our initial conditions begin. So we set this up in our equilibrium, right, where ammonia reacts with water to produce ammonium and hydroxide ions. And we're starting with that initial concentration. The change then, which way does it go? It goes to the right, because the hydroxyl is at 0. And then we get a loss of X on the left-hand side and a plus X and a plus X on the right-hand side. That sets up our equilibrium. Okay. Now that we know those concentrations, in order to use, well, we can go from Kb, right? Kb is going to be ammonium, right, on top, hydroxyl, and then ammonia on the bottom. And that's equal to 1.8 times 10 to the minus 5. That. And we substitute the values for each one of those in there. We estimate this one, the X, to be so small that it's insignificant because that value is so small. And then we solve for X, and X is hydroxyl ions. So we do POH and subtract it from 14, and we get pH of 9.56. Right? And I'm just telling you it satisfies the 5% rule. We can do the calculations, but that will take extra time. Okay. Or we could use the Henderson-Hasselbalch. Right? We've got these concentrations, but the acid is NH4 plus, which is on the right-hand side. And the conjugate base is on the left-hand side. So we can't use Kb. We've flipped the equation. We have to use Ka. So we take this Kb and we convert it to Ka. Right? Remember what Ka is? It's 10 to the minus 14 divided by Kb. So we divide, well, be consistent. We take this Kb and divide it into 10 to the minus 14, gives us Ka. Then we can use Henderson-Hasselbalch. And if we plug that value into Henderson-Hasselbalch, we get, well, the pKa, we have to find that and then take the pKa as 9.25. Then we can use Henderson-Hasselbalch, 9.25, and which goes on top? The conjugate base, the ammonia concentration, 0.0667 goes on top. And the acid goes on the bottom. Then we get the same value. So 6 of 1, half a dozen. Okay. You have to work a few of them before you get comfortable with it. That goes for anything in chemistry. Calculate the pH of a solution made by mixing 1 liter of 0.5 molar ammonia and 0.5 liters of 0.1 molar ammonium chloride. Then add 0.1 mole of HCl gas. So why do we do it as a gas? So we don't have to factor in a changing volume. Right. So we just bubble HCl through the solution and it dissolves in the water and doesn't change the final volume. So we don't have to worry about changing the volume by adding the acid, the HCl. We put it in there as a gas. That's for convenience, so that we don't complicate the calculations with a third addition of volume. Okay, so before we get started, we have 0.5 moles of ammonia, 0.1 mole of ammonium. And sometimes, in fact, I think, let's see, when are we going to do this one? That's our last lab. Complex ion lab. Sometimes it's more convenient and quicker to the end if you do the stoichiometry in terms of absolute moles. And then you take what you get at the end after the reaction and convert it into concentration. That's what we're doing here. So if we have 0.5 moles of ammonia and we add 0.1 mole of hydrogen ions from the hydrogen chloride, we're already at 0.1 mole of ammonium, then the reaction uses up the hydrogen ions and gives us 0.4 moles of ammonium and 0.2 moles ammonia and 0.2 moles of ammonium ion. Now we calculate the concentration. Right, there we go. So at this point, we have this concentration of our ammonia base and its conjugate acid, 0.133 molar. Now we can use Henderson-Hasselbalch, but we have to have the Ka again. So pKa is 9.25 for this reaction, and we plug it in the correct locations, and the pH now is 9.55. All right. Okay, here's a good one. What if we want to know the equivalence point for this reaction, acetic acid plus, let's see, yeah, acetic acid, and titrate it with 0.1 molar sodium hydroxide. We want to know what's the pH at equivalence. Okay, now why would we want to know that? Because the equivalence point has to be determined using a pH meter. And you have to titrate the curve to find the equivalence point. That's a lot of trouble if you don't have an automated system. Now, they do have automated systems that'll, with auto samplers, that'll do that titration. Just, it's a dumb machine. It'll just keep doing them and doing them. But if you have to do them by hand, and I've done hundreds of them in a day, I want something that works quicker. So we use an indicator. It'll change color when I'm close to the equivalence point. That's called the endpoint. Okay, so that's where my color change occurs. Well, we've got a whole host of different indicators that change pH at any given pH you can imagine. They change colors. How do I know which one to choose? I have to know what that is. And that's what the calculation does for me. It says this is where the pH is going to, this is the equivalence point. That's where your color change needs to occur. So once we find that, then we can go to our chart and find out what's the best indicator. Okay. So let's take this problem. If we have 100 milliliters of 0.1 molar acetic acid and with its Ka, and we titrate it with 0.1 molar sodium hydroxide solution. So we know that the equivalence point is going to occur when we have equal amounts of base and acid for the reaction. So when is that going to occur? Well, let's see. Do I do calculations? Here we go. We start off with 0.1 molar solution of acetic acid and 0.1 molar sodium hydroxide. So that means 0.1 molar acetic acid and 0.1 molar sodium hydroxide. What this is going to do for us is, since these are equal concentrations, at the equivalence, they're going to be equal volumes too. Okay, so we can actually pick any volume we want. Well, no, we can't, because we have 100 milliliters of acetic acid. So this is 100 milliliters. At equivalence, this is going to be 100 milliliters too, isn't it? Right, because they're equal concentrations. Okay, now we know that at equivalence, the volume is going to be 200 milliliters at equivalence. Okay, that's why we can say 0.1 molar times 100 milliliters equals 10 millimoles. Okay. So 10 millimoles divided by 200 milliliters is equal to 0.05 molar. Right. So what we're saying is we're gonna theoretically go to equivalence with this concentration, but once we get there, we're gonna say, all right, at that point, 0.05 molar acetic and 0.05 molar hydroxyl neutralizes. Right? We use up both of them. And that means that we end up with 0.05 molar acetate ion at equilibrium. Okay. Now the dominant reaction is that conjugate base is going to react with water. And we're going to end up with 0.05 minus some of it, right? And we're going to recreate some acetic acid and some hydroxyl. Okay, so we went all the way one direction, now we're coming back the other. And this is after the dominant reaction. Once we've created that acetate as equivalents, now we have that as our expression of concentrations. Okay, so this is a reaction of a base with water. So we need a Kb. We got the Ka. Now in this case, we're going the other direction. We need a Kb. So once we have the Kb, then the Kb expression is x squared over 0.05 minus x, or approximate to 0.05 in the denominator and x squared in the numerator. Then we can calculate POH. We have the OH concentration is equal to x, calculate the POH, then calculate the pH. So at equivalence, the pH should be 8.72. And then we look on our chart and say, all right, if that's our pH at equivalence, what's our best indicator? During first semester chemistry, we did a titration using phenolphthalein. I think it changes colors in the neighborhood of 9.2 or 3, something like that. So close enough. All right. So this is a comparison of titration curves depending on the Ka of the weak acid. So if we have a Ka that's in the neighborhood of between 4 and 5, then we get something, our acetic acid is right in here somewhere. And it's going to have an equivalence of 8 something. Okay, we can do the same thing. We can go backwards. If we start with ammonia and titrate with hydrochloric acid, then the equivalence point is the other direction. But it's still the inflection point. Notice that this is concave down and this is concave up. So that's the inflection point for this curve. And that's our equivalence point. Okay, here we have polyprotics. And remember, when we were talking about protons leaving a polyprotic acid, one proton at a time, and each one has its own K value. So for the first K value is going to happen at a very low pH for phosphoric acid. And our buffer region is going to be 2.16. That's the pH at pKa1. pKa2 for the second proton is going to be near neutrality. And the third is going to be at near 12.32. So that's why if you're involved in biochemistry or biology of any kind and you need a buffered solution, typically it's going to have phosphoric acid in it because it's so flexible. You can adjust the pH to give you a buffer pH near 2 or near 7 or near 12. All you have to do is just set it up correctly. But that's what a triprotic acid titration curve looks like. Okay. I already talked a little bit about indicators. The indicator is just a convenient way to gauge the equivalence point. If you're not interested in the rest of the titration curve and you only want to know something about the equivalence point, then use an indicator. You get there a lot quicker. The equivalence point and the end point usually don't happen at the same pH, but they're very close. close enough for government work. Okay, so our phenolphthalein, here's the concept here is indicators pH indicators undergo their own acid-base reaction. So it's almost like they're competing. The advantage to the indicator is even though it is undergoing this reaction, and our generic is HIN as the indicator, and then it loses a proton and produces a conjugate base, IN minus. Even though it does that reaction, it's a very, very small concentration. So it doesn't interfere with your titration. So if it's in its basic form, it's pink. If it's in an acidic form, it's colorless. And the Ka for this particular indicator is 4 times 10 to the minus 10. The pKa is 9.4. 9.4 would be, and these indicator acids are weak acids. So pKa for this one, that 9.4 would be its buffer pH. And this is just for general. This is what the protonated phenolphthaleins on the left and the deprotonated is on the right. And we see what's happened is this bond is broken. To remove the proton, it turned this one into a anion. And the proton left from here and broke that bond. What that did was it changed the light absorbing characteristics of the molecule. Okay, yeah. Profoundly changed the structure of the molecule. That's understatement. Now it absorbs light in the blue end of the visible spectrum and passes the red end. So that's why it turns pink. Okay. So let's see. Now we have to introduce concepts of physiology, because if we're talking about a color change, how efficient will our eye be in detecting that color change? So a rule of thumb is that the color change occurs, let's see, for this particular reaction, the color change occurs plus or minus 1 unit of pKa. So for any given pH, at say our equivalence pH is at a given value, 8.7 something, wasn't it? 8.73. That pH will be approximately the pKa of our indicator plus or minus 1 unit. So that's a pretty wide range, right? Because 1 unit is an order of magnitude, isn't it? Right? So it's like it's a 100 times change in concentration. So for the phenolphthalein, that range is between 8.4 and 10.4. And that covers the equivalence point for acetic acid. Acetic acid is right in the middle. Well, it's actually toward the lower end. But actually, that's preferred. If you're coming up from the bottom, titrating an acid with a base, Then you want the indicator to be slightly above. You want its pKa to be slightly above your equivalence pH. And that's where we're at here. If you were titrating a weak base with an acid, you'd want the pKa of your indicator to be below. Okay. So we can go to all the trouble if we know the pKa of our indicator, and some of them have multiple pKs, right? Because they have the ability to deprotonate 1 proton, 2 protons, more than one. It's more convenient to just use an indicator chart. That's what this is. So for our, if we're looking at phenolphthalein, it should be right over here somewhere. There. And it shows you the colors that develop in the process. So brom cresol green actually goes to yellow, green to blue in this range right here. And you can get combinations of indicators. Like one indicator, as long as their color changes don't interfere with one another, then you can get a change at lower pH of one. Well, the universal indicator has a mixture of several of these, and it goes through like pH papers that way. And you have to compare it to a color code. But this is the most convenient way to determine what indicator you need. This is when they change the color that needs to be close to the pH of your equivalence for the reaction. I think that's it. Yep, that's it.